Good afternoon, everybody, and welcome to the MTL seminar series. And today is my pleasure to introduce us John Kitching from NIST. The title of his talk is Chip-Scale Atomic Devices, Miniature Precision Instruments Using Atoms, Lasers, and MEMS. So I know John for many years because I work on technology that could be applied to his research. But for the rest of you who maybe doesn't know John, let me give you a brief introduction. John received his PhD in applied physics from Caltech in 1995, and he founded and is the leader of the Atomic Devices and Instrumentation Group at NIST in Boulder, Colorado. And he's in the Time and Frequency Division. So he, as in group, has done all this groundbreaking work on chip-scale atomic clocks and atomic devices since the early 2000s. And he continues to work on that kind of stuff, new compact, low-power precision instruments. So it's a great honor to have you here, John. Thank you for accepting the invitation, and the stage is yours.
Great, thank you. So first of all, you can see my slides here, I guess. My slides are good? Okay, and you can hear me. Very good. Okay, so thank you, Luisa. It's a great pleasure to be able to speak to you today, albeit from a couple thousand miles away. Yeah, don't worry about the title here. I somehow got the title confused, but in any case, yeah, I'm going to talk about work on kind of combining atomic spectroscopy and silicon micromachining and photonics to try to make very compact low power instruments that potentially have a broad range of applications. And so this is a very kind of multidisciplinary work, and I hope it will be interesting. And a lot of the last part of my talk will focus on new work that we've been doing in the last few years, which we're calling NIST on a chip, which is basically trying to see whether we can really kind of how many SI traceable standards we could implement in chip scale format. So I'm going to start with atomic clocks. This is kind of how I got involved in this area. I think many of you are familiar with timing references. Of course, the most common timing reference that we use in the world is the kind of quartz oscillator that is the basis of most wristwatches. Up at this end here, of course, there are the most precise timepieces that are available, and these are now kind of a new generation of optical clocks that has come online in the last 20 years or so. You may be aware that time is the most accurately measured physical quantity, and you can actually measure it now to about parts in 10 to the 18. And so these are spectacularly precise instruments. But the big problem, of course, with these is that these are basically sort of large laboratory that are required to sort of have all the pieces of these, and so they're very large and are rather difficult to deploy outside the laboratory. Now, there are commercial atomic clocks that exist, and the two kind of most common are the cesium beam atomic clock, which is a rack-mounted instrument, and vapor cell atomic clocks that are based on thermal vapors of rubidium or cesium atoms confined in a small cell. And you can see here that this is kind of the way things stood about 20 years ago. These were things that you could hold in the palm of your hand. They ran on about 10 watts of power, and they cost about $1,000. And they would give you some kind of timing precision to about 10 to the minus 10. Now, of course, timing is critical for a large range of different types of infrastructure. Probably the most common thing that we all know about is satellite-based navigation. The navigation system in your car or on your phone is all based on atomic clocks that are orbiting the Earth in satellites. But more than that, there are big applications in telecommunications, especially for atomic clocks. Cesium beam clocks are used for optical fiber telecommunications, and vapor cell clocks are most widely used in cell phone base stations, where the timing requirements are somewhat stringent, but not nearly as stringent as what you need for satellite-based navigation. And so there's lots of different ways in which these clocks really impact a lot of things that we sort of take for granted in our daily lives. Now, of course, over the last 50, 60 years, there's also been a real push to increasing miniaturization and mobility. So, back in the 1940s, we had, or 50s, I guess, we had computers based on vacuum tubes. And then this progressed to simple transistors, and now we have integrated circuits that can power, a very, very powerful computation device that you can use and run on a battery in your local coffee shop. Similarly, with communications, this is what a telephone looked like when I was growing up, completely analog thing. And now we have, again, very, very powerful communication systems that are available, all running on a battery and giving us vast capability. And even like in space science and space technology, it used to be that, most space missions were these massive, very expensive instruments that, were very, very carefully prepared and very expensive. And we're moving now into sort of an era where much smaller satellites that can be deployed in much larger numbers are gaining traction and becoming sort of more important. And so one of the questions that we ask all the time at NIST, we are in charge of developing physical standards for measuring things, and we're always asking ourselves how to adapt to this increasing need for mobility and lower cost that is kind of the way the world is just pushing us these days. So one kind of vision of like what we're trying to do in these devices kind of shown here. This was what a vapor cell atomic clock looked like back in about 1970. And you can see it was a rack-mounted instrument. The physics package is actually this kind of cylindrical thing up here. And then there's some quartz oscillators and a bunch of frequency multiplication chain and stuff. And over 35 years, this has progressed to something, again, that you can hold in the palm of your hand. The physics package is now roughly a couple of cubic centimeters. And what we're kind of going for here is a future where we might be able to sort of manufacture and produce these types of instruments in a way very similar to the way that integrated circuits or micro machined elements are made. And so we envision having kind of arrays of devices that could be assembled kind of at the wafer level using a parallel process to develop all these. And I could be using this slide for a while, and this is the kind of the same number I used maybe 15 years ago. So maybe this is going to be like 2040 or something like that. So we don't know how far we'll get here, and you can see that what we've made are some sort of baby steps along the way to this kind of vision. So I know a lot of you are not atomic physicists, so I'm going to just give you a little tutorial on atomic physics in one slide. We work mainly with alkali atoms, which are the atoms that are in the first column of the periodic table. And that means that they basically have a nucleus, they have some filled electron cells, and they have a single valence electron. And part of the reason we do this is because these atoms have a very simple energy level structure. There's only one atom really that participates in most of the interactions with optical fields. And so that means that we can have very, very precise control over the quantum state of the atom. Of course, atoms, the nucleus and the electron both have a magnetic moment, and they have angular momentum, they have spin. And so not only can they charge on the electron interact with the charge on the nucleus, but the magnetic moment of the electron can interact with the magnetic moment of the nucleus. And so, if we imagine we have this atom sitting here and we are trying to do something, we're trying to perturb it, well, we can shine various types of electromagnetic radiation on it. And one thing we can do is we can shine a laser on it, frequencies on the order of hundreds of terahertz, and photon energy is on the order of an electron volt. And this basically promotes the electron to some higher orbital that has increased energy. And this allows us to do for example, optical pumping, and also detect the quantum state of the atom in a very precise way. We can also shine microwaves on the atom, and those are frequencies in the gigahertz range. And basically what these do is they flip the spin of the electron with respect to the spin of the nucleus. And so the internal energy is changed by this spin is on the order of a microelectron volt, or corresponding to frequencies on the order of a few gigahertz. And then finally, we can put the atom in a magnetic field. And of course, an atom in a magnetic field, it has angular momentum and it has a magnetic moment. And so it will precess in that magnetic field. And we can excite that precession by driving it with a transverse oscillating magnetic field that essentially will drive the atom to process about this magnetic field. So there's lots of different ways. Well, these three ways are the main ways that we sort of can kind of interact with the atom and use it to measure things or to time things. So why are atomic sensors interesting? Well, this is kind of the main reasons I believe. You know, one of the things is that we can get exceedingly long coherence times with these systems. So electrons in alkali atoms can have coherence times in the sort of milliseconds to seconds range, and quality factors of 10 to the 8, sometimes even more. Nuclear spins in atomic systems can last for days. If you polarize them, they'll sit there polarized, at least in certain forms, for quite a long time. And if you add laser cooling and trapping and go to optical frequencies, you can achieve quality factors that are sort of approaching 10 to, or even above 10 to the 15. So this is basically, you know, an optical field oscillating at 10 to the 15 hertz, confined for on the order of a second. And so because we can get these, you know, massively high coherence times, this leads to very good sensitivity, leads to good short-term stability for clocks. But perhaps another, and perhaps even more important aspect of atoms is that the transition energies or the frequencies that are needed to excite transitions between those different energy levels are all based on fundamental atomic constants. And so, for example, the Zeeman Hamiltonian, which basically governs the interaction of some atomic spin with a magnetic moment in some magnetic field, you know, the Hamiltonian gives you all the dynamics of the system, and the constant of proportionality here, the thing that is scaled, everything scales with, is this constant mu. And this is just a bunch of fundamental constants that, as far as we know, are not changing in time or in space. And so what that means then is that, you know, an atom that you, you know, probe here on Earth is the same frequencies as you would probe on the moon, and it's the same now as it will be in 100,000 years. And of course, people, you know, in the physics community are always looking for some kind of variation of these fundamental constants, but so far nobody has been able to find any. And so we can sort of take this parameter mu as being a fixed constant set by quantum mechanics and nature, and because that now determines the entire energy level spectrum, it means that you know, if once you measure these quantities, now you can have a very, very direct relationship between, for example, the magnetic field and the energy level structure. And you know, and so by measuring the energy level structure, you can then accurately measure the magnetic field. And so this is sometimes why we refer to this as a quantum technology. It's because the quantum mechanics really has you know, major implications with regard to SI traceability and accuracy and realizing the base SI units. And then finally, atoms, because of their very high Q factor, have very high nonlinear optical coefficients, and so you can do various types of things, various nonlinear processes with very low power levels. Okay, so the other element of our work is silicon micromachining, where we basically you know, form physical structures in silicon using lithographic patterning. And so the standard technique is you put a photoresist on silicon, you illuminate it with sort of light or electrons through a mask, and then use some kind of etchant to etch out physical structures where the mask has been, where the photoresist has been exposed. And of course, you can make lots of different complicated, this is some little chips that we made very early on in our work 25 years ago. But of course, MEMS is a critically important thing in your airbag accelerometers, gyros in your phone, and accelerometers in your phone, and lots of other applications. So, you know, it's again a major field, major technology field that again is working and really impactful in the real world. So what we did about 20 years ago was to figure out a way to make these very, very small vapor cells. And conventionally, you know, the way that the vapor cells were made for atomic clocks and other sensors traditionally has been using glass blowing techniques. And basically what you do is you take a glass tube and you fuse on windows, and then you have this filling tube and you attach that to a vacuum system, and then you pump out all the air in it, and then you distill your alkali atoms in, and then you seal it all up. And so this is kind of a bad picture of one of the vapor cells in our lab, but you know, this is a very time-consuming process. If you want to buy one of these cells, they cost about $500 if you buy them from a commercial company. And so it's not a very great way of sort of making cells for these types of instruments. So what we did, again, some years ago was to figure out a way to use silicon micromachining to make these vapor cells. And the basic structure is shown here. We start with a piece of silicon. We etch a hole in that silicon, roughly 1 millimeter thick and 1 millimeter across. And then we bond glass onto the top and bottom layers and confine the alkali atoms and buffer gas, if we want, inside this kind of hermetically sealed volume. And these are pictures of cells that we made, again, a long time ago. And so the process itself is kind of the, is all the detail in it. And I'll show you how that works. We start off with what we call a preform, which is basically a piece of glass that's bonded to silicon. And we use anodic bonding, which is a method of bonding glass to silicon that involves heating it to about 300 C and applying about 1,000 volts across it. We then put this preform into a vacuum chamber, and then we have an ampule. And this ampule contains a mixture. So this is the glass ampule here with a little nozzle coming out, open at the bottom. And this ampule contains a mixture of barium azide and rubidium chloride. So rubidium chloride is just a salt, and you can dissolve it in water. And barium azide is actually an explosive. It's also used in airbags, or it used to be. And basically, these two chemicals, if you heat them up to about 300 degrees C, they will react, and they'll form barium chloride, nitrogen, and pure elemental rubidium. Now, rubidium is very reactive. It'll react with oxygen and water, and so you have to put it in a vacuum chamber. Whenever you're handling pure rubidium, you can't expose it to air. So all this is done in a vacuum chamber, and so we heat this cell up, and then we deposit it down into the bottom of the vapor cell, deposit the rubidium down into the bottom. We then move this ampule out of the way, backfill with some gas if we want it, and then finally do an anodic bonding step in the vacuum chamber to make the sealed cell. So this is how we've been doing this for years and years, and we can kind of make cells 1 or 2 or 3 at a time. Recently, we've and this is actually new work that is just about to come out. It's been accepted for publication. We've developed a process for making large wafers of these. And so the basic conceptual idea is instead of having the ampule kind of above the cell, we kind of flip it over and make it part of the wafer that contains these holes, and then deposit the alkali atoms on the underside of this glass wafer. And so I'll show you how this works. So we have an array of holes in the silicon, and they're actually pairs of holes, one large one and then one slightly smaller one. And this is a whole array of these kind of pairs. And then what we do is we deposit the precursor material, this barium azide and rubidium chloride, in the small set of holes, okay? So again, this is stable in air. You can do all this in air. We have an automatic machine that goes and just does this. And then we put this in a vacuum system, and we put a glass wafer down on top of the silicon, but we don't bond it yet. Okay, and instead what we do is we heat this wafer pair up, and what that does is it heats this up to its reaction temperature, this precursor stuff, and then it reacts, and rubidium then goes and it goes up and sticks on the lower part of this window, and then we pull the window up. The nitrogen that's produced in this reaction all escapes. The barium chloride stays in the cell. And then we move this over inside the vacuum system. So now the rubidium is sitting inside the vapor cell. And then we do the final anodic bonding step and finally dice the whole thing up to make small individual cells. And all this can be actually done now in a commercial anodic bonding tool. And so for many years, our process was a little difficult to transfer to anybody else because it was a custom vacuum apparatus, and it was difficult to operate and stuff. And this is now all works in a commercial bonding tool. And so in principle, if you wanted to do this, you can just buy the bonding tool, and then we can give you a recipe, and you can do it yourself. And so this is an example here of vapor cells that we've made. This is actually 499, I'm told, vapor cells on here. I don't know why the graduate student didn't actually add one extra vapor cell to make it a clean 500, but anyway. And actually we tried to fill about 350 of these, and of these we were able to measure that 109 of these cells had rubidium in it. Here's a picture of one of them. You can see the rubidium metal that's condensed on the lower window of the glass, kind of silvery stuff there is rubidium. And we're able to get a pretty good uniformity in buffer gas pressures from cell to cell. And so this is now enabling us to make large numbers of cells. And you know, it takes us about a day to make these roughly. And so it basically reduces the cost of the cell from $500 to basically zero. You know, we can make kind of an infinite number of these now. And so that's a good thing, right? Because now it means that any instrument that's made using this technology is potentially, you know, much lower cost, and so this is a very exciting development in cell fabrication over the last couple of years. Now, these cells have been used in a variety of things. The first thing that we made was an atomic clock. And the basic idea, the structure of this clock is there's a laser down here at the bottom, a vertical cavity surface emitting laser. The light is emitted upwards through the vapor cell and is detected in a photodiode. And the basic idea is that you modulate the laser with a frequency on the order of, say, 6.8 gigahertz, which corresponds to this hyperfine transition in the rubidium atoms. And when you scan the frequency of your oscillator, you basically get a change in the response of the atoms. And you can use that then to lock up the oscillator to the atomic transition and make an atomic clock. And so this is kind of a picture of one of the, I think this is the second one we made that shows the basic device here. It's about the size of a grain of rice, roughly, maybe 1.5 millimeters on a side. And this particular one ran at about 75 milliwatts of power. So these are now commercial products. And so the kind of history of this, we began working on this in the late 2000s. DARPA funded this in the sort of mid 2000s. And in the end, there was a product that was released. There's actually two products you can buy now, one made by Microchip and one made by Teledyne. NIST has the patent on this. And these hold, you know, the basic idea is these hold 100 microseconds over one day on only 120 milliwatts of power. And so if you kind of look at this in the context of historical atomic clocks, that one that I showed you in the early view graph, that rack-mounted clock ran on about 40 watts of power, and that was released in about 1970, 5065. And then you can see over 40 years, the power consumption of various atomic clocks kind of dropped maybe to about 10 watts. CSAC is down here at 120 milliwatts, and so it's a 30 times reduction over any previous atomic clock, and it means you can run it on a battery. And these are used now, I think the main application at the moment is for underwater oil exploration, where you essentially use acoustic waves that are sent down into the ocean floor, and they're reflected off various rock strata and oil fields and things. And you put hydrophones on the ocean floor to sense these seismic waves, and you have to have them all timed well. So atomic clocks are good down here. There's no GPS, of course, underwater. And as of this year, they've now sold, the companies that make these have sold over 120,000 units, and they're about $1,000 each. And so this is resulting in about $100 million of economic impact. And so it's kind of got to the point where this is now, I would say, a successful commercial technology, and it's quite widely used in a lot of different things. I mentioned that, you know, we used to you know, take pictures of these things all the time with various food items, and I guess in the MEMS community, people like to use coins. For some reason, we got stuck on food, and so this is a picture of one of these clocks with a grain of rice sitting here, and so you know, these pictures kind of made the rounds back in 2005 or something like that. And after the commercial product release, somebody took this picture here with some of these commercial CSACs with a whole plate of sushi. And you know, there's actually is one of these tiny clocks inside here somewhere that's about the size of one of those grains of rice. So you know, there's kind of an amusing little food-related anecdote. Okay, there are on the order of 30 research groups worldwide that are now working on some versions of these types of clocks, including Draper Labs in the Boston area. I know they're connected with MIT. It started really in the United States and then spread a few years later to Europe, and now there's actually a lot of activity in China and Japan developing these things right now. And there's kind of a nice review paper, if you're interested, that I wrote a couple of years ago that is a pretty complete review of kind of all the activities that have been going on in the last 20 years in this field. One kind of historical note, so I showed you the second physics package we built, and then the first one was not nearly as pretty as the second one. This is the picture of the first one, and this is the kind of thing I remember we got it working the day before Thanksgiving in 2003. And I remember going into the lab on Thanksgiving morning in 2003 just to play with it a little bit for a couple hours because it was so interesting. But you can see it was pretty hideous structure. But it turns out this is actually now on display in the Smithsonian Air and Space Museum. And so you can actually, on a mall in Washington, D.C., so you can actually go and see this thing. And I'm always very grateful that, they don't have a magnifying glass or anything. This little tiny little speck here is the chip scale clock, and not exactly our best work, I would say, but anyway, there it is sitting on a mount in the Smithsonian. We've also been able to develop atomic magnetometers using this same technology, and the basic idea is that a clock measures a frequency very precisely, or generates a very precise frequency, and of course anything that perturbs that frequency then can be measured also very precisely. And so by switching to sort of magnetically sensitive transitions in the atoms, we can make magnetometers, and they're kind of similar in structure for the most part to the clocks. And we can get sensitivities down at the sort of femtotesla level, or tens of femtotesla per root hertz level, which is within a striking distance of squid-based sensors. Squids, of course, are superconducting quantum interference devices. They are they're the gold standard for magnetometry. But of course, they need cryogenics, right? They need liquid helium things, and so they're very cumbersome technology. And so these atomic mags now are competing with squids, and they've actually been, so these chip scale devices have actually been commercialized now by a number of different companies. Twinleaf, QSpin, and Geometrics were sort of the three that have been doing this. And just recently, there's a company called Kernel that just released some things earlier this year, some information about their work. I think they're connected with MIT also. Brian Johnson is the guy who actually is leading this whole effort. He's sort of a dot-com billionaire, and trying to really revolutionize brain sensing using this. And in fact, our group has done some work in this also. We were able to show that we could measure brain magnetic fields. And this is actually some work actually really using these QSpin devices where you have a fair number, a few magnetometers sitting in some kind of a helmet, and now you can measure magnetic fields from the human brain in a highly mobile environment, so people can actually do things with their, while they're being monitored. And this company, Kernel, I think, is trying to make this so you can actually walk around with these things on your head outside and still get monitoring of your brain magnetic fields. So it's kind of opened up, I think, a new sort of opportunity in neuroscience and in brain monitoring. And this is continuing to be a very, very active area. All right, let me turn now to NIST on a chip, which is kind of the thing that I've been really focused on over the last few years. And kind of the idea with NIST on a chip is kind of to ask, okay, we got these clocks, we have these magnetometers, how many other things could we measure or sense using this type of technology at the chip scale? And so what I'm showing here is a picture of a few different instruments. This is a fountain clock. It's sort of the best representation of the second that exists right now. This is an optical lattice clock that is basically a wavelength reference. This is a watt balance, which realizes the kilogram now, connecting it with the Josephson junction voltage standard and the quantum Hall resistance standard. And then finally, this is one of these Josephson junction voltage standards. And these are all SI traceable standards. These are all things that basically connect some physical measurement to the definition of that value as the SI tells us. And so the idea, okay, these are all great instruments, but they're, big things, right? So the kind of what we're trying to do in this on a chip is to ask, okay, like how many of this type of thing, how many of these units could we realize in a chip scale format with SI traceability? And the idea is we'd like to kind of embed these into instruments. And so, one way of thinking about this is in terms of calibrations. Calibrations are a big business. If you're a machine shop and you got your set of gauge blocks and it slowly over time drifts out of calibration, then you get it recalibrated. And so you basically send it in a package to a calibration lab, and then they return it to you they measure it against their standards, and they return it to you with some document that says, here's how long your gauge blocks are. And this happens, a huge amount of time, right? These things need calibrating all the time. And in fact, these calibration labs, reference their instruments to us at NIST, and so they send us things, and we calibrate them and send them back. And apparently at NIST we get like 14,000 things a year to calibrate. And of course our job is to connect the things that we build to the SI in some way. And so this is kind of our role. But this whole chain here is just a hugely expensive and cumbersome thing, and it takes huge amounts of time and stuff. And so the idea with NIST on a chip is, if we could build something that had the SI traceability built into it, like this part here built into the chip itself, then these things could be manufactured at low cost, and they could just be sent to people, and they could do the calibrations themselves, or even better, just build the thing into an instrument. Imagine every optical spectrum analyzer had one of these wavelength references in it, and now this thing is calibrated for the lifetime of the instrument, and there's no need to send it off and have it recalibrated all the time. So this is kind of the vision, and my management sort of calls this zero chain traceability, meaning that we don't have any chain here anymore. It's directly traceable. And I don't know, we kind of imagine sometimes, like every gas pump and grocery store scale and everything is calibrated by one of these 10-cent chips, and then there's no need for anything, and you get your gallon of gas exactly as it's supposed to be and stuff. So okay, so this is kind of the big long-term vision of this stuff. So what are we actually doing? Well, in our work, kind of what's inside this is kind of two things. There's we've designed this in such a way that we have this kind of atomic cell layer, which is really the SI traceability. This contains the atoms, the quantum systems that are going to give us this SI traceability. And then we're integrating this with photonic systems, essentially single mode photonics that allow us to route the light around on the chip and essentially be able to make sort of more complex structures using lithographic definitions of patterns and stuff like that. So that we could make complicated things here on chip, basically. Part of the reason I got excuse me, I got interested in this some years ago was because I kind of looked at how many different units you could potentially realize, and it turns out you can do quite a lot of them. There's only 7 base SI units that you need to realize most physical measurements, and it turns out we can actually do basically 5 of these. We can do frequency, as I've described, with an atomic clock. Length can be done by essentially locking a laser to some kind of an atomic transition in a vapor cell. And because that transition frequency is defined by quantum mechanics, now if it can be measured with respect to the SI second, the frequency of that can be measured, then you get an accurate wavelength reference. You can do temperature. Basically, atoms in a thermal vapor, of course, are moving at some velocity. There's some Boltzmann distribution, and that produces Doppler broadening. And so if you measure this Doppler width of this thing, you can connect this now to the thermodynamic temperature, again, just by fundamental constants and frequency you have to measure. So you can do temperature, and you can do current and voltage by looking at, again, the effect of magnetic fields on the atomic energy levels and the effect of electric fields on the atomic energy levels. And these can be, of course, translated into current and voltage by measuring some dimensional quality somewhere, quantity somewhere. So there's lots of different things we can kind of do here. And so, it's kind of, at least to me, kind of interesting because you really can get a long way into metrology and address a lot of common problems with a very simple thing, this microfabricated atomic vapor cell. I'm going to focus on length. So we made an early decision to go with, that you can kind of choose. Silicon photonics is all great, works at 1.5 microns, but there's not very many good atomic systems there. These are some molecular systems that are good, but they're a little hard to deal with, and they don't have very strong absorption. So we've been focusing on silicon nitride photonics and connecting that with rubidium and cesium, which have transitions in this wavelength 700 to 900 nanometers. And so this is the focus of our work over the last few years. I mentioned wavelength references. So wavelength references are a fairly widely used metrology tool. They're used in sort of positioning systems. They're used for actually wafer positioning and semiconductor manufacturing, where you need very, very accurate and precise positioning of the wafer. And the kind of industry standard right now is actually the Heaney laser. And this is a picture of one of them. They're, I don't know, a couple of meters in size. It's actually a kind of a vacuum tube that's in there, right? It's a helium neon tube. And so this is kind of widely used in the market. It's pretty big. And so we want to kind of make something that's, cubic centimeter in size, and we actually can do better, we think, than the polarization stabilized Heine in terms of accuracy. Make something that's much lower cost also. And so one of my colleagues who works on Heine lasers calls this the Heine killer, is what we're kind of building here. So we're doing this with integrating atoms with photonic systems, and there's actually a number of groups that are kind of working in this area right now. Israel, Germany. This is a group at IBM doing methane detection. And one of the key things here is, so some of these techniques are based on, single mode silicon nitride waveguides that have an evanescent field that, of course, is above the waveguide. And if you put a rubidium vapor over here, then the light senses the rubidium that's near the waveguide, and so you get absorption and things. And one of the problems that you have, of course, is that the rubidium atoms are flying through these fields at 300 meters per second, and so they might only spend a nanosecond in the evanescent field here before they hit something like the wall or whatever, and that destroys the coherence. And that means that you get kind of very broad resonances, right? That you can measure them only for a nanosecond, so they're going to be kind of gigahertz scale resonances. So this is kind of the line width that you get from these types of systems here as a function of the size or the dimension, linear dimension of the field. So evanescent fields are kind of down here. They give gigahertz wide lines. This line is 300 meters per second. Glass cells, of course, these are centimeter scale things, and you can get tens of kilohertz wide line widths. And we're kind of working in this intermediate region here from like 10 microns to a millimeter, where we can use these MEMS cells, but we also get access to some interesting atomic resonances, Doppler free transitions in alkali atoms, and then there's sort of 2 photon transitions and molecular transitions and the like. We've had this nice collaboration with a group in Gaithersburg that makes mode converters, essentially to make, we're doing this by essentially having the waveguide, and then it goes into a grating coupler that essentially diffracts the light upward out of the chip. And so they've been able to make grating couplers that have nice big beams on the order of 50 microns, 100 microns. And so that kind of pushes us down on this line here to get better performance. And we've been able to make wavelength references using this. So here is an example. This is a photonic chip that has these silicon nitride waveguides on it, and then they go to these grating couplers that diffract the light upwards, and then they go through this vapor cell. And using this, we can do spectroscopy, optical spectroscopy of the atoms, and we can lock our laser up onto one of these nice narrow resonances, and we can get stabilities kind of in the 10 to the minus 11 range. This is kind of what the laser does if it's just free running, and then we lock it up and we get a factor of 200-300 improvement in the stability. And the accuracy now is kind of 10 to the minus 9, which is even now, without even trying, we're already better than the Heine laser. So this is something that we're pushing forward, is trying to address the length metrology. I'm going to skip this. We're also making chip scale optical clocks, and so as you may know, for the last 60, 70 years, time has really been realized by microwave clocks, so looking at microwave transitions in atoms. And just over the last 20 years, with the advent of optical frequency combs, now optical transitions can be used as clocks, and of course, because the frequency is 5 orders of magnitude higher, now you can essentially get much better performance. And so we are now building chip scale optical clocks. This particular one is based on a 2 photon transition in rubidium. Essentially 2 778 nanometer photons excite the atom up into a fairly high lying level, and the atoms then decay by emitting a fluorescence at 420 nanometers. And so what we do is we take a laser at 778 nanometers, we send it into this vapor cell. This 2 photon transition happens, and now the atoms fluoresce blue, which we then detect with a micro PMT. And so here are some of the devices. This is the DFB laser. This is still a bulk component. It's a big sort of, well, few millimeters optical isolator. We have one of our MEMS vapor cells with a nice wall coated AR coating on it, and then one of these micro PMTs. And so put all these things together, and we can measure these nice narrow optical lines. This is again at 385 terahertz, and we get like a 1 megahertz wide line. And then we can use that to make a clock. And so this was kind of a big collaboration with, actually led by Draper, but also including Stanford, Caltech, Yale, and a couple of other groups at NIST. And so basically what we did is we took this optical standard, and so we locked our laser up to one of these really narrow lines, and then we divided it down to the microwave using a cone system that was based on microfabricated optical resonators, very, very high Q optical resonators. And so basically these generate combs that allow us to essentially divide this optical frequency down into the microwave region. And so here's kind of some of the, this green line is kind of the chip scale clock data, and our work, this particular paper here that was published last year achieved this kind of stability, and we've actually now improved this down to even better. So this is now 3 orders of magnitude better than a chip scale clock in terms of stability. And so, and so this is kind of maybe the future. It's not an easy thing to put together. These combs are a bit hard to work with, and kind of getting everything working takes several racks of electronics and stuff like that you never see in the pictures. But this actually was kind of a nice piece of work, and we were actually awarded just a month ago the Paul F. Foreman Team Engineering Excellence Award, and this is pictures of all the people who contributed to this at all these different places. And so it's very nice to get a kind of a team award. It's a very, very complicated thing to build, and you really need to have experts in a lot of different areas. And it was just great working with this team, everybody working together to make this kind of function. So how does this clock compare, right? So so this is a kind of a plot that shows the stability of various types of clocks as a function of integration time. And so, like vapor cell clocks are about 10 to the minus 11 at 1 second. They integrate down for a while, they start to drift. This is kind of the stability of most cesium beam clocks. These are very good at long integration times. There's hydrogen masers. Hydrogen masers are, of course, like the size of a small filing cabinet, roughly. Fountain clocks, again, even commercial ones are similar size. And our kind of chip scale device is now kind of sitting down here, roughly. And this is actually the optical standard, not the cones included, but the cones basically shouldn't degrade this at all, I don't think. And so now we're getting something that's pretty close to hydrogen maser performance, filing cabinet size, and something that's actually pretty small. And so we can actually, we think, push this down even more using some new ideas. And so this is now something which is now, you can see, orders of magnitude better than a chip scale clock. There's still a ways to go, I would say, on this in terms of getting it to be something that could be commercial, because the cones, it's just hard to integrate these things together. And so, but in any case, I think there's perhaps a good future for this technology. All right, so I'm just going to sort of conclude here. I've talked a lot about sort of atomic systems. The vapor cell is really a very simple way of getting your quantum system and then basically having it to use. And the atoms in there basically can be excited using lasers and the like. And really it's that kind of the quantum mechanics in that really gives you the accuracy, the stability, and of course the nonlinearity, as I talked about. So what we're trying to do then is to integrate this with photonic systems and with silicon micromachining to make things that are, manufacturable, that are compact, that are low power, I think I think this is going to still keep going in the coming years, and the fact that the chip scale clock and the magnetometer technologies have been commercially successful is a good indication that these things don't just work in the laboratory, they work in the real world, and they are making a direct impact in to various applications, which is always kind of nice to see. It's sort of the proof of the pudding in some ways. If you're doing what you're doing is good. So just to acknowledge the team, and this is a bit of an old picture, but I really want to acknowledge the staff members I work with: Matt Humman, William McGeehee, Tom Hevner, and Susan Shima. And Liz Donnelly worked in my group for many years. She now got herself promoted, and so now she's not, but she did a lot of work also. And we've worked with a huge number of former NIST collaborators over the years, and we again have a lot of collaborations with various people. We're always looking for postdocs, so if you're interested in this, kind of gets you excited, then send me an email. I'm happy to talk to you more about it. So thanks very much. I'm happy to answer any questions.
Sorry, thank you, John, for the very exciting talk. And yeah, we're open for questions right now. We can start with the ones of the Q&A. So there is a question of the audience that I also had, John, and it's about the yield when you described that the new way to make the rubidium cells had 31% yield. So I was wondering if you could give us some more details into that. So was that meant to happen? Is a low yield because of something that you identified?
Yeah, no, I mean, we want to get a higher yield for sure. We'd like to get 90% or above if we can. So this was sort of our first, well, not our first attempt. We made about 10 runs, 10 wafers of these, and 8 of the 10 failed completely. We didn't get any rubidium, and 2 of them did work with both with yields of about 30%. There's nothing really fundamental about this. So usually, what we have found is that the main sort of failure mechanism in these cells is that there's just no rubidium in there when we finish the bonding process. And we think that that has something to do with either the amount of precursor material that we put in the, in the small cavities, or perhaps maybe some oxidation process that happens as we transfer them. These are very small amounts of rubidium, so if you have any kind of contaminants in the cell, then it can basically cause the rubidium to disappear. So I don't think this is in any way fundamental. It's just that we just haven't perfected the process. There's lots of different things you can adjust in the process. So basically, what you do, right, is you do the process, but there's kind of temperature ramps and voltages that are applied, and there's a lot of sort of tweaking that you kind of need to do to sort of get it all to work well. And so we just haven't done that. We actually got to this point about, I don't know, a year ago or something, and then the pandemic hit, and we just haven't been able to work on it since then. This has basically been closed for most of the time. And so I don't think there's anything fundamental here. We just need to kind of refine the process a little bit to increase the yield.
Okay, so the next question in the Q&A is actually related to that, and they're asking you if maybe you can remind us if you said it. So why the two-step process? So why you have to do the deposition on a smaller cell and go into various steps to put it eventually to a larger cell? So that can be just done in one shot?
Yeah, right. So actually, the cells that I showed you here, let's see, these ones. So these ones were actually made these were made years and years ago, by using this direct process where we actually deposited the precursor materials into the cell, and then we just kind of heated it up as we bonded it, and then they released rubidium. And it did work in the sense that the rubidium was in there, but what we found is, so in addition to the rubidium, there's of course this gas that evolves in the cell. And when you make an atomic clock, the presence of the gas actually shifts the clock frequency. And the amount it shifts the clock frequency depends on the pressure of the gas inside the cell. So if that's changing in any way, what's sort of happening is the clock frequency will drift over time. And when we made a clock with these cells, we saw exactly that. We had a massive drift of the frequency over time. And we attributed that to the presence of these sort of the residual chemicals in there. For example, if this barium azide, if there's still some left over, that can slowly decompose and produce nitrogen. Or if there are other contaminants that can sort of suck gases or getter gases. So that it's important that you keep this cell as clean as possible, at least for the clock applications, because if there's anything chemistry that's going on in there, then it's going to give pretty substantial shifts. And if those are large, then it becomes sort of, there's no point. You may as well use a quartz crystal if you're doing that. So this process, avoids that. We keep the precursors in a different location, and that's why we did this. We did it with this technique here.
Okay, so well, let me see. There's maybe a third question, Q&A. Yes, so from there, it says, one of the figures showed a getter material. Is it something that is necessary for long-term stability?
Yeah, well, yeah, it's more about the line width. So, so you're referring to this thing here. So the way that we actually introduced the rubidium in this particular cell was using a technique that was actually developed by a French group at Femto ST in Besançon, France. And they, following on our initial work on these cells, they basically found a way of, you can get these dispenser pills, which are basically it's an alkali chromate or molybdate. So it's a compound of rubidium or cesium, and it's got this zirconium aluminum reducing agent. And it's kind of a packed kind of pill basically. And if you heat that pill up to about 500 degrees C, then it releases rubidium. Any of you have used SAYS getters? That's basically the stuff that's in the SAYS getter that produces rubidium. And so what we do to make these cells is we don't deposit the rubidium. We actually have one of these pills that we just handle in air, and we stick it in the cell. And then we bond the cell closed under vacuum. And then we send a high power laser in here that heats up this pill to its reaction temperature of like 500 C or something, and then it produces rubidium. And what we found is for these types of experiments where we're looking at optical transitions, we need to have very, very low buffer gas pressure, sort of below a millitorr roughly in the cell. And what we found was that when we did this activation process, we got resonances that were more like 3 or 4 megahertz wide. They should be, the natural line width here is about 300 kilohertz. And so, and we attributed that to that when we heated up this pill, there were gases that were evolved in that process, and that was broadening our line. So it wasn't so much shift, it was more that the resonances were broadened. And so then we started introducing these getters, and what we would do then is to activate the pill to produce the rubidium, and then using the same laser, we'd activate the getter to suck up any residual gas. And that's how we got these much narrower lines. So this gave us about a factor of 4 improvement in the line width. And so the getters are important for cells where you don't, where you want to have very, very good vacuum other than the alkali atoms. For cells for for the conventional microwave clocks and for magnetometers, we don't bother with the getters. They're just not needed.
Okay, so let me see, one more question from Michael. How much of the entire clock system can be assembled at the wafer level? So it's an issue of integration.
Yeah, that's a really great question. So I've been putting this picture up. Let's see, wherever it is here, my picture of of these wafers of cells, right? And my vision, right, was, and again, this goes back like 20 years, was that we were going to be doing this, assembling devices where, this thing here is our cell wafer, and then we'd be assembling this with wafers of lasers and optics and stuff like that. And it's not done that way in the commercial world. The cells are fabricated at the wafer level, and some of the optics, I believe, is, but then there is sort of a pick and place process that goes to actually assemble the clocks. And of course, then you've got to put the clock on a thermal suspension, and then and as you go outward from the device, less and less of it is at the wafer level. And part of this is driven, I think, by kind of market volumes, right? I mean, so these companies, they sold what I say 100,000 of these things over the last, say, 5 years or something like that. So that's like 20,000 a year. And so, at that level of production, it is probably more sort of economically, reasonable to have a fair amount of pick and place going on in there. And so, but I do think that, we're actually in my group right now, we're developing magnetometers where we're trying to, again, expand out, right? We can do the basic stack at the wafer level, but we want to now do the whole thermal suspension at the wafer level. And we're trying to develop kind of processes to do that. And I think it's possible. It's just not clear exactly how useful that will end up being, if it's expensive to implement, if there are yield issues, and ultimately, when you're selling a product, this has got to be reliable. It's got to work, right? And so, right now, I think sort of with the quality control issues and stuff, it may be better to stick with the more conventional assembly techniques. But I think this is, again, the end goal that we'd all like to get to, right? It's just that we haven't quite got there yet.
So I have a quick question related to what you just said. It's about the materials, about the geometry. So I recall for example, the work of Andrei Schell. They have these dome-shaped cells and well, etc.
Yeah.
And in MEMS, historically we heavily use semiconductor technology, and it's a great thing and a bad thing. It's a great thing because a lot of people thought into it, and it's a mature process, but maybe restricts the kind of things we can do in terms of the material, the shapes. So do you have any thoughts on that? So are there any materials you would like to process that you can't, or any geometry that is very hard to implement with the current approach?
So, sorry, Luis, I'm having a little trouble hearing you. Can you just summarize the question again?
Oh yeah, no. If you had a wish list of materials and geometries that you would like to make better devices, but that you cannot make because of the technology,
because of the way we do it. Yeah, I mean, so the stuff we did with Andre was actually really, it's probably the coolest cells we've ever made. These little bubbles basically that have rubidium in them, so one of the important things. So right now with this particular design, right, we can get light in through the glass, but we can only really put it in from one direction. And there are certain types of devices that you want to make where you want to have counter-propagating beams, or sorry, perpendicularly propagating beams, laser beams. And so those cells that we made with Andre were designed for that purpose. Since they're a bubble, like a little glass bubble sitting above the substrate, you can kind of have beams coming in from multiple directions. And there are other ways to do that. For example, you can put in angled walls inside the silicon that can redirect the light. And so that is one thing that has been again developed by people over the years to kind of enhance this and allow for multiple directions to go in. And I guess it allows you to have some improvements in the device performance, but it also adds complexity. And one of the really, really critical things in this technology is how simple it is. I mean, this clock, is just a stack of glass and silicon, and there's not much. There's a laser, there's a photo detector, and then there's just a bunch of glass in there, right? And so, and that's one of the things that I think has led to the widespread adoption of this technology. Is it's just not very complicated. And the more things you add, the more laser beams you add, like adding one extra laser in this thing, like changes the business case completely. And so you really have to be careful about adding complexity. And many people have worked on different improvements of cells and also different ways of interrogating the atoms and stuff. And it's just very expensive to go and change your design and adopt these things. So I think there are valuable things to be done, but most things you can do with a single laser beam, and then you're working a little bit around the fringes and stuff like that. We have been able to get AR coatings and high reflectivity coatings on this. Yeah, I mean, again, I would say the biggest challenge right now is this wafer level fabrication, and getting the cost down is probably the biggest thing. Well, so one of the other things we would like to do is to move to different types of atoms or molecules. For example, if we could put acetylene in a cell, in a MEMS cell, that would be interesting, because acetylene is a molecule, of course, And it has sort of rotational vibrational transitions that are in the sort of 1.5 micron range, which is really useful for telecom. Now, acetylene has a whole other set of problems, but you know, that's, you know, maybe that kind of thing would be of value also, I think.
Okay. So, well, I don't know if we can squeeze one more question, and it's from the audience, and it's about electromagnetic shielding and its relationship with sensitivity. Would you like to comment on that?
Yeah. Yeah, sure. So, so RF sensitivity is not really a big issue, but DC magnetic fields for these types of clocks are. We use transitions in the atom that are first order insensitive to magnetic fields, but magnetic fields always you know, give you second order perturbations, and those second order perturbations can shift the frequency of the resonance and basically cause you know, shifts in your clock frequency. At the sort of accuracy levels that you need to achieve sort of the 10 to the minus 12 stability, it turns out the shielding is not that important. So in fact, in these chip scale devices, I believe that this is just packaged in a this outer case here, or maybe just a slightly, you know, slightly smaller inner case is just made out of mu metal, and it just shields DC magnetic fields, and that works well enough. A simple shield works well enough to achieve the kinds of performance that you would like to get out of the clock. For the optical standards, it's much less important is magnetic shielding, because the transitions 5 orders of magnitude higher. You know, G factors are all, you know, megahertz per Gauss, and so you got 5 orders of magnitude higher frequency. It just doesn't matter that much. Of course, for the magnetometers, you want no shielding at all, right? Because you want to detect a magnetic field. So you'd have to you have to pay a little bit of attention to that, but I would say it's not a kind of a major challenge.
Okay, thank you, John. Well, we run out of time, but we would like to thank you again for this very exciting talk, and congratulations for your award from the Optical Society. Like, that was amazing work. And for the audience, thank you for holding with us and holding on with us. And we'll see you in the next MTL seminar. Everybody have a great rest of the day. Thank you so much.
Thank you all. All right, see you.